All right. Hi, everyone. Happy Tuesday. So just some updates for the class regarding Thursday's lecture of this week. So next lecture is pre-recorded. We will not have live class because I am traveling to the East Coast and the time zone difference is very hard for me. So I've already recorded that and it's posted under the recordings pages already. So you can watch that after this class today. And homework number 2 is due next Tuesday. It's already available, but you can ask questions about that starting next, or this week and whatnot. Okay, so without further ado, let's get started. We have a guest speaker today for the second half of the class, so I want to make sure we get through everything. So today we're going to start talking about our cryosphere. And this is actually a graphic made by our guest speaker showing some information about our Arctic sea ice. So let's take a moment. Let's look at this data and this figure and write up what you think we are looking at in this data. So I'll give you about a minute and a half here, and then you can enter your answer and your thoughts into the chat. All righty, so yeah. Yep. Right. So, and I'm sure Zach is going to talk a lot about this and these figures that he makes and posts on his Twitter account. But what it's showing you is January on the x-axis, it's showing you months of the year, January all the way back to January. And it's showing you the amount of sea ice extent, basically how many million square kilometers of sea ice do we have over the Arctic each month of the year. And you'll note, and some of you did, that there is a pretty obvious seasonal cycle, right? There's more sea ice in the winter and there's less in the summer, which makes sense because we know our North Pole, the Arctic, gets blasted with sunlight during the 24-hour days of summer. We look at the data here, the range of data is showing you basically, the median, which is average, or the middle of all that data. And then we have some variability. And this year, 2023, is starting to fall. And this is, a month ago now, showing us that 2023 is at the low end of all of the data that we have. So this year is exceptionally low. It's falling outside of the range. It's kind of in that 90th percentile for extreme. So quite a bit of low amounts of Arctic sea ice extent. Okay, and as I mentioned, our guest speaker will talk a lot about this today and why it matters for the Arctic climate. Okay, so today we're going to talk about our first half of the cryosphere lecture. We'll talk about the different time scales that we have cryospheric components, talk about snow cover and permafrost, and really how climate change is impacting permafrost and why it's so important for us to better understand that feedback scenario. So the cryosphere, when we use the term cryosphere, it's not always considered one of the major spheres of the Earth system, like the atmosphere or the biosphere. But the cryosphere is basically water in its solid form. So ice, and where we have ice on our planet, right? So our big ice sheets, Antarctica and Greenland. We also have frozen water as snow and and glaciers. Okay, so water in its solid form. So we have things like our big ice sheets. There's snow on top of those ice sheets. We have icebergs and sea ice, that frozen ocean water, land and river, or excuse me, lake and river ice, snow on our mountains, permafrost, and glaciers and ice caps. And we're going to talk a bit about all of these in the next few lectures. So when we think about the cryosphere, different components of the cryosphere are going to exist or last for different amounts of time. And so this is showing us the different time scales that each part of our cryosphere kind of exist over. Which part of our cryosphere has the longest lifetime or exists for the longest amount of time? Alrighty. So when we look at this, right, we have our different components. Snow is typically a days to months, right? Seasonal. So is our sea ice, months, several months. What is actually existing for the longest amount of time is really our ice sheet. So some of our ice over Antarctica is well over 2 million years old, meaning it fell, what is now ice, it fell as snow 2 million years ago and has been preserved because it's so cold. Okay, so our ice sheets are thousands of years, thousands to really millions of years old. And that matters because that helps really control some of our climate in terms of being a big component of our total albedo. Okay, so here are some of our cryosphere components. Today we're going to talk about sea ice and permafrost and snow, and we'll talk about glaciers on Thursday in that pre-recorded lecture. So snow. Snow is very short-lived in terms of its residence time, right? It can snow one day and the next day that snow melts away. Here's a satellite image, the visible satellite image looking down on Earth after a snow event. And we can see, right, there's a lot of spatial and temporal variability in snow cover. Snow has some interesting properties, though. It actually can change the temperature of the air and the ground because of these properties. So thinking about snow for a second, the underlying surface, for example, the soil beneath snow, is it going to be generally colder than the air, or is it going to be warmer than the air temperature? So imagine what's going on beneath the surface where all this snow is. Is the soil going to be colder than the air or warmer than the air? Okay, so this one is fun because snow is actually insulating. And what that means is it is trapping some of the heat that's deeper within the earth. So the earth is always giving off heat. And so what's happening is when you add some snow, the soil beneath the snow is actually, on average, warmer than the air above the snow. Okay. And that's kind of cool, which means if you're ever trapped in the snow, you can make a snow cave. Okay, so here's an example of this snow cave. You dig a hole and you have a little vent for air so you don't uh, asphyxiate from lack of oxygen, but it acts as an insulator and it helps keep heat from escaping from the soil. So if you're ever trapped, which God forbid you're never in that situation, but you can make a little snow cave and it'll help keep you warmer than if you were just out in the elements. Okay, so snow acts to kind of keep the soil a bit warmer, which, as you can imagine, has important impacts for ecosystems, right? In places that get annual snow cover, that soil might not get frozen because it has that insulator and it keeps the soil from losing so much heat. Okay. But on the opposite, snow has a high albedo and it's going to keep the air above the soil cooler during the daylight hours. So it's going to keep the air above the snow cooler, and it's going to keep the soil beneath the snow warmer. And so after it snows, sometimes the coldest days are right after, like the next day after a snowstorm, because the albedo's high and any of that incoming sunlight gets pretty much reflected back. So especially here in Colorado, our coldest days are usually right after fresh snow. And then a few days later, it warms up again, but that snow has a super, super high albedo. So kind of countering effects, whether or not you're in the surface, the soil, or if you're above the snow in the atmosphere. Now we can look at trends in our snowpack, right? Because snow is so variable, both in time and space. And every year we can see differences. And this year is kind of an anomaly in the positive sense that there was a lot of snowfall. And many of you are probably familiar with this, that California got a lot more snow than usual because of some of those atmospheric rivers that were bringing a lot of moisture into the Pacific Northwest. But if we look, right, so there are places in the Sierras that had quite a bit of snow. But overall, when we look at the Western United States from 1955 through 2022, we see that a lot of our snow areas in the high elevation mountains are actually seeing quite a significant negative percent change, meaning these places have much less snow than they used to in the 1950s. Okay, and that makes sense because it's getting warmer. And so snow, the precipitation that's falling is not always a snow anymore. Oftentimes we're getting more rainfall rather than snow. Okay, that's snow. That's all we're going to talk about with snow in terms of its importance. It's very important, but it changes so much. It is a very variable part of our cryosphere. The next part that is more long-term is permafrost. And so permafrost is defined as permanently frozen ground for at least 2 years straight. And so here are some images of permafrost up in Alaska and Siberia. And you can see these wedges of ice, and this is the frozen soil underneath the surface. And so this is what we mean by permafrost, permanently frozen ground. So where would we find permafrost? Well, it can occur on land around the Arctic, also around Antarctica and South America, in places wherever the summer heating is not getting deep within the soil. And that's the main thing, is it is okay for the top portion of the soil to thaw during the summer. And we're going to talk about that active layer. What matters is that with depth, deeper into the ground, that soil stays frozen. That's the permafrost. So we even have some permafrost under shallow areas of the Arctic Ocean because we have ground and soil underneath that area. Okay, so you can see here the different types. We have isolated, sporadic, continuous, and what does that mean? It's basically just how, what is the horizontal extent of the permafrost beneath our feet. So continuous permafrost is this area here on the left, which is no unbroken layers, very thick, horizontally expansive permafrost. It's even found under small lakes. And this permafrost was formed during the last glacial period of about 25,000 years ago. And so it's this area in the Arctic has stayed cold enough that this area has not thawed. Discontinuous permafrost is in the middle of this diagram, which is basically there's pockets of unfrozen ground and then pockets of frozen ground. Okay, these are typically thinner sections, thinner in depth permafrost, and these were formed in the last few thousand years. They're not as old. And then we have sporadic permafrost, which is areas of frozen ground, just small areas. So here you can see sporadic is just like here and there. There are just random pockets, not so random. There's obviously some reasons why, but there are these pockets of sporadic frozen ground. Now, as I mentioned, in the summer season, the upper portion of the permafrost can thaw, and that's known as the active layer. So here in this cross section, we can see the top of the ground here, the soil and the grass, and we have this area that is no longer frozen. It is thawed out. And then we have the ice wedge beneath. So the active layer is the upper layer of permafrost that thaws during the summer months when there's summer heating from the sun, and then it refreezes during the winter. And the reason we call it active is that our permafrost contains a lot of stored carbon, stuff that hasn't decayed or hasn't been decomposed yet. Reason for that is it's cold. And that process of decomposition requires temperatures above freezing. And so there's a lot of carbon within our permafrost, within that soil. And in the summer months, when this active layer becomes deeper, it's active, the microbes, the bacteria, those things that are trying to break down that carbon can go to work. They become activated. So that's what we call the active layer. Now, I keep using the term thaw versus melt, right? So thaw is the terminology we use for a solid that warms above 0 degrees Celsius, right? You don't say your chicken breast melted, right? Even though it became above freezing, you say, I thawed the chicken breast. So when we say melting, we're talking about a phase change from solid to liquid, like water, it melts. But thawing is where you take a solid and you warm it. So in this case, our solid is the soil. So you can't melt soil, you can thaw the frozen soil. So why would permafrost thaw? Well, we can add heat to the permafrost, to the soil, by that incoming solar radiation, getting that heat from the atmosphere and our sun, especially during the summer. We also have heat coming from Earth's interior. That's known as geothermal heat. It gets hotter as you go down towards the center of the Earth. Earth's core, inner core, is as hot as the sun and the size of the moon. And so that heat is coming up to Earth's surface. And we call that the geothermal gradient. So as you go deep, 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 deep into the soil, you actually will start to see and measure some of that geothermal heat that is coming up out of Earth's interior. So when we look at some ground, some soil profiles, we will get some temperature variability with depth. Okay, so here we're going to look at this ground temperature profile on the right, which shows a few lines. And I'm going to focus our attention on the first line here, which is on the left. Okay, this left line is what we call the minimum winter temperature. Okay, so we have depth here. So this is the surface. And then we're going deep into the soil. So in the winter, the temperature gets really cold. And that temperature is coldest near the surface, where Earth is losing heat to the atmosphere via conduction. Okay, so the coldest temperature will be near the surface. And then we have the next line, which is the profile we get during the summer. So in the summer, the upper portion thaws, okay? And you're gonna see the warmest temperature again near the surface, because that's where a lot of the heat is coming from in our system here. It's coming from the sun. And so you get what's kind of like an umbrella, where you get your coldest temperature in the winter and your warmest temperature in the summer. But what you'll notice is that at some point those two lines meet up. And that's the depth in our soil where the permafrost knows nothing about what season we're in. Okay, so there's some depth, it's called the depth of zero amplitude here, where that temperature profile change, either in the winter or the summer, makes no impact. Okay, it's right here in this case. And we also have the 0 or 32 degree F line marked here. Okay, so this is our 32 degree F. So if the soil temperature is above 32 degrees Fahrenheit or 0 degrees Celsius, that soil is thawed. If you're to the right or below that line, that soil is frozen. And so you can see that we call the active layer anything, any depth, above that point. So when the active layer, that temperature profile crosses the 0 degree line, anything above that is considered active. It's above freezing. We can also look at this and figure out where our permafrost base is, right? So I mentioned that we're getting some heat from the Earth's interior, that geothermal flux. And so if we go deeper, 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 we see that there is a point towards the bottom here where our profile of temperature actually crosses back over that 0 degree Celsius, 32 degree Fahrenheit line, temperature line. And that's from the geothermal heat. Okay, so as you go much deeper into the ground, the temperatures start to increase, and you can see that with that profile. And so this would be the base of the permafrost. Anything below, anything deeper, will be unfrozen or not frozen because it's getting too much heat from the Earth's interior. Okay, so this is a profile of a permafrost situation. So what are some factors that affect permafrost depth? Well, obviously climate, right? What is the temperature? What is the annual temperature in that region? Is it getting cold enough to sustain this depth, this thickness of permafrost throughout the year? Okay, so basically your annual temperature, which I forgot to tell you is this line, this third line here, I'm going to mark it with green. This third line is the annual temperature. So when you take the winter temperature, summer temperature, fall and spring temperatures all together, they have to average and allow for the existence of that thick permafrost layer. Right, so it has to have a good climate to allow that permafrost to exist. The soil moisture, the soil has to be wet enough, moist enough to freeze. The soil's too dry, not enough moisture, you won't get that freezing because it's really the water inside the soil that helps get that freezing. What vegetation there is, topography aspect, are we north slope facing or south slope facing? How much sunlight, because it matters, especially in the northern hemisphere, as well as southern, but in this case, we're focused on northern. And also lakes and rivers. Why? Because water has a high specific heat. And so the specific heat, that high specific heat of a lake will radiate some of that heat, conduct some of that heat, and potentially keep the soil from freezing. Okay, so here's another one of my cross sections that I drew. Looking at my cross section, okay, so we have our winter temperature and our summer temperature. Can you tell me what is the depth of the active layer in this location? All right. So the active layer is the depth of soil that gets above freezing during the summer. So when we're looking at this, we kind of have to hone in on our 0-degree profile. So our 0-degree C, which is freezing, is this line here. So what depth does the temperature cross that 0-degree line? And that is going to be our active layer. So in this case, it's right here. 1, 2, 3 meters. So a lot of you said 7, and what you were probably looking at is this boundary, which is that point on the umbrella. But that is just where the depth of the temperature change occurs during the summer season. But if you look, all of this area from 3 to 7 in the summer is still below freezing. Okay, so when we're looking for active layer, we're looking for where the summer temperature profile is crossing that 0-degree ISO line or temperature line. Now, at this location, what is the depth of permafrost at the site? Or maybe better said, what is the base of the permafrost at this location? All right, so when I'm asking for the depth or the base, we're thinking about the bottom. Where is the geothermal heat causing the soil to thaw and become unfrozen? And that's going to be towards the bottom here, where our annual temperature profile of the soil crosses back over at that 0-degree line. Okay, so you can see here, if we go back up, that's our 0-degree C line. Anything beneath, any soil beneath 25 meters will be unfrozen. So if we're thinking about the depth of our soil, the depth of our permafrost in winter, well, it's going to be 25 all the way up to the surface. Okay, so it's 25 meters in winter. And then in summer, we said that the depth of the active layer is about 3. So that means the depth of our permafrost, or the thickness of our permafrost during summer, is 3 meters down to 25. So it's 22 meters in summer. Okay, so that means 3 meters, 9 feet of the soil becomes active in the summer, allowing those microbes to start breaking down that carbon. When we think about how climate change is impacting permafrost, what we're going to do is we take that annual temperature profile, the middle line, and you shift it, the whole thing gets shifted to the right, right? The whole annual temperature is increasing. Now, I've exaggerated this quite a bit, but the point here, right, is the whole temperature profile shifts to the right, gets warmer, which is going to have a few impacts. The first now is that we're going to, have the same type of umbrella in the summer and winter. And in this case, because temperatures warm so much, there will be a lot of active layer now. Okay, so the depth of the active layer will get deeper during summer if air temperatures get warmer. And the base of the permafrost gets shallow. Now, obviously, I said I exaggerated this, so let me unexaggerate it so that we can do a better example and show. Discard. I just put a line here. So if we do something more like this, even just 1 degree warmer annual average temperature, we can now see that the base of the permafrost, this whole thing is going to change. It's going to be more like purple. It's going to be more like this and more like this. Okay, so our depth of the active layer gets a little deeper, and the base of our permafrost is shallower, which also makes sense because temperatures are warming, so we're going to have less thickness of our permafrost. Okay. So some signs that we see observed change in permafrost are moving from grasses to more shrubs and trees. The reason for this switch from grassland to shrubbery and trees is that the active layer is thickening. And with that thicker active layer, vegetation that has deeper roots can sustain. So we have seen in the Arctic, for example, places that used to only really have grass with thin, shallow root systems are now being replaced with trees and bigger bushes and shrubs because that active layer is even thicker. Other changes in permafrost are what we call drunken forests. So these are where, as the soil is thawing and you get that liquid water, it starts to move a lot. Okay, so solid, cold, frozen ground, pretty stable, like an ice cube. But when you start to melt, you get liquid, the pore spaces, the soil starts to move a bit, and the trees become kind of wonky because the ground starts to move. You can also get a lot of sinkholes in land subsidence, for example, here. And you can actually see some of that frozen ground there, but the active layer is getting deeper and the ground starts to move a bit more. Other changes include changes to the infrastructure that was built on permafrost. So for example, here we can see the shifting railroad lines. Okay, not good for trying to transport materials and goods. Also not good is homes that are built on permafrost are now collapsing because the ground surface is evolving and changing. Now, people live in areas with permafrost, right? Many people live in the Arctic, a lot of whom are indigenous and are now being impacted by this thawing permafrost. So sinking and movement of land will impact and has impacted homes, the structural integrity of homes and roads and many other infrastructures. So you can see here this home sinking because the permafrost beneath the soil has thawed and maybe even completely disappeared. Also, other impacts are that a lot of communities and indigenous peoples in the Arctic use underground freezers, right? Because there's this frozen soil beneath their homes. And so they can use these underground freezers, nature's freezer, to store food over the seasons. But now that's actually becoming difficult and sometimes non-existent. So I was watching a documentary, and folks said they used to store some of their meat down in these permafrost freezers, cellars, but now they can't do that because it's thawed. And so you're changing a way of life for these folks. So there's some ideas here to help reduce impacts on permafrost. For example, this specialized raised rail bed is helping to kind of keep the permafrost, this is in Tibet, from thawing. And I mean, this is interesting, but the main issue with the permafrost thaw is that the Arctic is seeing amplified change due to climate change. And so its temperature change is accelerating much faster than the rest of the world. And again, I mentioned some of this permafrost formed thousands of years ago. So it's not something that can reform instantly. So here are some observed changes in permafrost. So this is showing subsurface temperatures to about 10 meter at around 10 meters depth. So we can see basically anything below 0 would be permafrost. So all of these sites have permafrost, but we can see some of the sites are seeing rapid increases in temperature, for example, in Norway. And we can also see that same line just smoothed a bit more. So pretty much any place we have measurements of soil temperature below the surface, we are seeing increases in that temperature. Now, of course, we don't have a whole lot of data because it's really hard to get into this permafrost area, to these extreme remote environments in the Arctic and in Siberia, for example. So our data is a bit more limited than, say, the atmospheric measurements we have around the world. But the measurements we do have show this impact. Okay. When we think about the future, again, this is a report, a figure, excuse me, from the IPCC special report on the ocean and cryosphere. So they did a whole series analysis on just ocean and cryosphere impacts. And you can see, based on our different scenarios, a low-end future of carbon emissions and a high-end future carbon emissions. We can see how much permafrost area change is expected. The high-end scenario is like 75% decrease in permafrost. And the low end is still about 25 to 30% decrease. And you can see that even though we stabilize our carbon emissions, there will be this kind of consistent and stable change because, as mentioned, it takes a long time for permafrost to grow. The soil has to get back to below freezing. Okay, and if we look at Alaska, again, we can look at different emission scenarios into the future, and this is taken from the National Climate Assessment Report. We can see the soil temperatures across Alaska in our different emission scenarios. So in the bottom, again, lower carbon emissions, we stop emitting carbon, high emissions at the top. We can see that the soil temperature in the southern portion of Alaska, even in our low emission scenario, is now well above freezing. So the freezing line here is kind of that yellow to purple. And we pretty much see all of the southern portions of Alaska becoming above freezing, the soil. So much, much permafrost thaw. And if you go to the higher emission scenario, even more. Okay, so we talked about that, but why? Why does this matter? Well, as I mentioned and hit upon, but we're really going to get into now, is that permafrost contains a huge amount of organic carbon. So all of those shrubs, all of that grass, all of the vegetation that has existed in that area, once it dies, it doesn't decompose, or it only decomposes a little because the temperatures are so cold. But when that active layer in the summer occurs, when those temperatures of the soil become above freezing, carbon is emitted either as carbon dioxide or methane during the respiration process of the bacteria and organisms that are doing this decomposition. Now, methane and carbon dioxide are greenhouse gases. Okay, so respiration happens in our soils as the microbes, the bacteria, the fungi, the algae, and many other things are breaking down organic matter to obtain energy, right? So they take up that carbon, produce a little CO2, soil respiration to create their sugars for their survival. Now, microbes will carry out respiration to obtain energy. And if oxygen is available, the product of that respiration is carbon dioxide. But if oxygen is not available, say it's saturated, there's a lot of water, it's below a lake, in a lake, then you don't get oxygen as a product, or excuse me, you don't get, carbon dioxide as a product, you're going to get methane. And that is called methanogenesis rather than respiration. Here is important to note the difference in carbon dioxide and methane as greenhouse gases. When you look at them over a 100-year time period, methane is about 25 to 30 times more potent, more powerful as a greenhouse gas than a molecule of carbon dioxide. So when we emit a lot of methane, the impact is more immediate in terms of global warming, greenhouse gas effect. Okay, so what determines whether or not our thawing permafrost is going to give us a lot of methane or a lot of carbon dioxide has to do with whether or not there's oxygen in the system. And that's not something we know, right? We don't have measurements of how much oxygen is available. Okay, so permafrost and climate, our microbes are going to eat up that organic matter when the permafrost thaws, gets above freezing. If there's oxygen, you get respiration and CO2 is emitted to our atmosphere. We get a greenhouse gas. If there's no oxygen available, we get methanogenesis, we get methane, again, a greenhouse gas. Yikes, either way we go, we're still getting a greenhouse gas. So recently, this little baby mammoth was found in the Siberian permafrost. Why is it so well preserved? Okie dokie. It is because it's too cold. So one of the reasons we have really amazing fossil records, well-preserved animals from the last ice age, is because this baby mammoth that is, from 30,000, 25,000, 16,000, whatever, thousands of years ago, it died and its body was not decomposed and it got preserved in that permafrost. Okay, so just imagine all of the other carbon of living things being our biosphere, the plants, trees, shrubs, all of that material for thousands of years has accumulated in that permafrost. Okay, so I have this fun video about researchers going to different places in the Arctic looking to understand, to better quantify what are we going to get? Are we getting methane? Are we getting CO2? And what that could mean for our climate in 20, 30 years.
This
Oops. Let me just make sure I shared sound. Yep. Okay, here we go.
This region may hold the key to the future of our climate as global warming takes hold. It's one of the remotest and coldest places on the planet. For much of the year, temperatures fall to minus 40 degrees Celsius, freezing everything solid, including the ground. But hidden in this frozen ground, known as permafrost, is a potential climate disaster. It's called methane, and it's a far more powerful greenhouse gas than carbon dioxide. The danger is, if the permafrost was to melt as a result of global warming, it could release methane on a massive scale. Ecologist Katie Walter believes that it's already beginning to happen. She's studying the lakes that cover the region.
The permafrost contains a very large pool of organic carbon. It's dead plant matter. And that dead plant matter, when it is thawed out in the bottoms of the lakes, it's a food source for organisms that produce methane. They eat the dead plant matter and they burp out methane. Methane is the byproduct of their digestion. And it bubbles up from the lake sediments and gets trapped in the ice.
If Katie's right, then the ice should be full of bubbles of methane. To find out the extent of the problem, Katie and an assistant head out onto the middle of the frozen lake. First, they remove the snow covering the ice, before using tea from their flask to clear the surface.
You can actually see the bubbles trapped in the ice. They're beautiful. The ice can be crystal clear with little bubbles, almost like coins stacked on top of one another. And what's happening is that as the bubbles are released from the sediments beneath, they wobble up through the water column and they hit the ice that's forming and thickening overhead. And so the bubbles actually freeze in place.
The trouble is, if these are bubbles of methane, it won't stay trapped in the ice for long. When the ice thaws in spring, the gas will escape. There's one sure way to check just how much methane is in these bubbles, because it's highly flammable.
When you poke a hole into those pillows of methane, you get this stream of gas that comes out, and depending on the size of your hole, you can get a very large stream of gas. So when you light that, you get a very large flame. And you have to be careful because sometimes you can singe your eyebrows.
These bubbles can be found all over the place. There must be enormous amounts of methane being released here.
That's it. Okay.
Go.
And that has serious implications.
The methane then heats the atmosphere, contributing to global warming, which then causes more permafrost to melt and more methane to be produced, and it's sort of this vicious feedback cycle. We think of this permafrost here like as a time bomb waiting to go off.
And it's potentially a very big time bomb. This great frozen expanse covers an area of well over 9.5 million square kilometres. That's bigger than the United States. If all the permafrost were to melt, then it could release enough methane to raise levels in the atmosphere by 10 times. That would be certain to speed up global warming. But by how much and with what consequences, nobody can really say yet.
Okay. And the reason we can't say yet is because we just don't know how much, one, total permafrost there is. right? We don't have expansive measurements, and we also don't know if it's methane or carbon dioxide. Okay, so here's our feedback loop. Temperature increases, the amount of permafrost will decrease, right? So that's a negative coupling. The amount of permafrost decreases, well, then our active layer becomes larger because temperatures are increasing. So that's a negative coupling. Our active layer increases, then the amount of photosynthesis or methanogenesis will increase. Positive coupling there. The amount of carbon, whether it be methane or CO2, in the atmosphere will increase. Positive coupling. And that leads us to a resulting increase in temperature because of the greenhouse effect. Okay, so a positive feedback loop, a big and important one in terms of climate change. So, future of carbon in the permafrost. Questions we have to answer is how much carbon is being released due to the thawing permafrost, and how old is that organic matter, right? Is it super, super old? Are we bringing carbon back into the game, the system that's been locked away for millennia? Or is it carbon that's only decades old, right? Because that's a big difference in terms of our carbon cycling. And so we have to try to answer those questions. And the way we can do that, it's pretty fun, is, and this is done actually, several groups at UC Irvine, one of them in the Earth Science Department, Dr. Shimshik's group, they fly these airplanes up over the Arctic and the permafrost areas, and they fit these planes with sensors to be able to measure in real time carbon dioxide and methane as they're flying over all of these land features. The plane takes in air, and then you can measure the amount of methane and CO2. Get about a measurement twice per second, which is pretty cool. And then what you can do is you can create these maps that show enhancements of methane above the background levels. Okay, so you have to make some measurements to kind of get a sense of, well, what's the air? What's kind of the average in this area in terms of methane level? And then you can get an enhancement. So how much extra methane do we see, which can tell us if methane is being released in a certain region of this area. Okay. And the way we find out if whether or not it's old organic matter decaying is by using radiocarbon or carbon dating. The way this works is by using isotopes. Okay, so we're going to pause here and have a little bit of a recap on isotopes from basic chemistry. But isotopes are the same element. The only difference is that there is an additional number of neutrons in that atom. Okay, so we're talking about carbon here. Most of the carbon in our Earth system is carbon-12, meaning it has 6 protons, 6 neutrons. You add 6 and 6 together, you get the 12. That's why we call it carbon-12. 6 protons, 6 neutrons in the nucleus. It's a stable compound. It doesn't decay. It is there. Anytime we're hanging out, 98.9% of the carbon in our Earth system is this 12 carbon, carbon-12. There's also naturally occurring carbon-13. About 1.1% of carbons in our Earth system have an extra neutron in the nucleus. This is also a stable form of carbon. It's not going to decay. It's not going to change. It stays the way it is. A very, 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 very tiny amount of carbons in our Earth system are carbon-14s. There are 2 extra neutrons. 6 plus 4 is 14. This is the radioactive version of carbon. And we call this radiocarbon because it's radioactive. And what happens with radioactive material is we get this decay process. And this decay process is occurring because these 2 extra neutrons make that atom, make that atom's nucleus unstable. Now, the rate of decay, this carbon-14 turning into a nitrogen-14, that process is predictable. And we know how fast or how long it takes. And we call that the half-life. And the half-life is how long, physical time, seconds, years, days, it takes for half of our initial carbon-14 atoms to decay to the the nitrogen-14 atoms. And so with that known half-life, we can make measurements of the numbers of carbon-14s versus the number of nitrogen-14s, and we can figure out how long ago this carbon existed or was formed. Okay, why is that? Because all living things, you and I, trees, cows, we're all taking up modern carbon-14 right now because carbon-14, radiocarbon, is produced in our atmosphere. It's produced in our atmosphere when cosmic rays from the sun collide with a nitrogen-14 and you get this carbon-14. So it's constant. We are in sync with carbon-14 in our atmosphere right now. So the radioactive measurement would not show any time because we are modern. We're talking to the atmosphere right now. But as soon as we die, the carbon-14 that was in our system, we stop taking up that carbon-14 and that clock starts ticking on that decay process. Okay, and so if we start with some known amount of carbon-14 or just 100% carbon-14, after one half-life, there's 50% of the original carbon-14 remaining. That 50% got transferred into or turned into nitrogen-14. And so you can see this decay process of carbon-14. We know that the half-life, the time it takes for half of carbon-14 to decay, is about 5,730 years. So now imagine I go out and I collect a sample of permafrost and I find that 25% of my original carbon-14 remained in the sample. How many half-lives of carbon-14 decay occurred in that sample? All right. So after one half-life, we move down to 50%. And then after another half-life, we lose half of the original 50%, and then there's 25. So every half-life, you're dividing by 2. Okay, so the answer would be here, 2 half-lives. Okay, which means that sample was 5,730 years times 2 years old, which is about 12,000 years old. That's how we can carbon date things. Now I test my sample, a different sample, and I find that it's about 17,000 years old. How many half-lives did the carbon-14 undergo in this sample? All right, so we're going to work in a different direction on this problem. We know the age now, and if we said it's about 17,000 years old, Then we would divide by the half-life of the carbon-14, so 5,730 years. That's going to give us the number of half-life, which is about 3. Okay. Now my next question for you is carbon-14, or can carbon-14 be used to date very ancient Earth materials, say, million years old? All right. So the answer here is actually no. Why? It has to do with how much original carbon-14 is left in your sample after so many half-lives, right? Because you start out with 100%, then you go to 50%, then you're 25, and then you're 12, then you're 6.5, and then you're 3%, and then you keep going out. Eventually, after about 10 half-lives, only about 0.1% of the original carbon-14 is still present. And any further half-lives, any further going back in time, any older than about 57,000 years, we just don't have the analytical precision on our instruments, on our tools that are making these measurements to distinguish enough to have good measurements. Okay, so we could make better tools, better mass spectrometers. But right now, our mass spectrometers that do these measurements are phenomenal. They take up whole rooms. There's one in the basement of Crowell Hall, an accelerated mass spectrometer. And so we'll probably never really get better than the 57,000 years. So carbon dating, radiocarbon dating, is only useful for things that are less than about 50,000 years. There are other naturally occurring radioisotopes that allow us to date things older, like uranium and thorium dating. That is used to understand things that are millions of years old, for example, in caves, looking at cave speleothems. Okay, and by the way, I'm going to post about this. One of the UCI professors in the Earth System Science Department, Dr. Kathleen Johnson, was interviewed for Jonathan Van Ness's. He's one of the Queer Eyes on the Queer Eye Show, but he also has a podcast for his podcast. And she talks about her research in caves and understanding climate change by looking at caves. So I'll post that. It's a pretty cool listen. Okay. So can we figure out if old organic matter is decaying in the Arctic? We can go out and make measurements of methane, and some of that methane will have some 14 carbon in it, and we can figure it out, okay? What we found, this paper is from a former UCI student, graduate student. They found that a lot of the carbon coming out of the Arctic right now is very young carbon. Okay, it's not super old. It's pretty much less than about 2,000 years old. It's not carbon that was stored during the last ice age, which is a bit promising news in terms of our carbon cycle, but we are still going to keep making these measurements so we can better understand the carbon cycle. Okay, so our guest speaker is going to be joining us in about 10 minutes. What I'd like you all to do is have a nice break. So why don't we all join back in around 2:50? Okay, so let's join back in 15 minutes. And then our guest speaker, who is an expert on Arctic climate change, is going to talk to us about what we're seeing in the Arctic. So please come back at 2:50 so you can hear from Dr. Laib.
Thanks for having me. Okay, let's see if this works. It kicked me out a minute ago. How about that? Okay. All right, thanks for having me. So hi, everyone. So I'm joining you from Princeton, New Jersey. So yeah, as was said, I'm a scientist at NOAA's Geophysical Fluid Dynamics Laboratory and also Princeton University. I have this super weird affiliation, and but I'm going to be talking about some of the research I do and also some of the science communication I do, which relates to all of this about Arctic climate change. Did the slide change, hopefully? One time I gave a talk and it didn't for a half hour. So anyway,
Yes, you're good. You're good.
okay. A little bit about me. So like I said, I'm over here in New Jersey. So I did my PhD, like it was said, at UC Irvine, and then I briefly lived in Colorado sort of during 2021, 2022, was a research scientist at Colorado State University. But I really think of my work, I think one of the awesome things about being a scientist is you just don't always do one thing. So I don't consider myself just a researcher, but I also spend a lot of time doing science communication and doing things like guest lectures. So I think that's one of the awesome parts of being a scientist is sort of all the different avenues you do in sort of your day job. So I often have a difficult time sort of explaining what I actually research. So as you know, I'm going to be talking about the Arctic, but I'm very interested in a lot of topics, and I've tried to distill them down into sort of a simple explanation when someone asks me for my elevator pitch on what I study. And what it really, I consider it being is I disentangle signals from noise. What I mean by that is basically all of my work and the themes of it is trying to understand what is caused by human-caused climate change versus just sort of day-to-day weather or natural variability. And I'm mostly like a modeler, so I work on the computer all day long, and I've been recently getting into things like machine learning and artificial intelligence. And the way I kind of use it is as sort of a statistical tool to try to extract those climate change signals from the noise. And I use data sets like climate models, and I use things like observational data sets. And I'm really interested in global climate. So again, like I said, I often have a hard time distilling what I study, and that's because I'm interested in way too many different climate topics. You can pretty much talk to me about anything related to climate change, and I'll become interested in it. But I'm going to be focusing on my work related to the Arctic, which is what I really studied during my time at UC Irvine. And I think every single presentation I've ever given about the Arctic, I sort of start off with these couple slides coming up. And I start off with this key fact, and it's that the Arctic is warming more than 3 times faster than the global average. So what this means is, the Arctic is warming so much faster than everywhere else. And this sort of terminology that we often use is called Arctic amplification. So the meaning of Arctic amplification is actually just that the Arctic is warming a lot faster. Of course, there's many reasons for this, and I'll touch on a few of them, and you might have already covered some of them. But simply, when you hear Arctic amplification or polar amplification, it just means that the polar regions are warming faster than the global average. And often when we sort of talk about the statistic, we show some sort of graph. I show one here. I intentionally don't have any labels here, and you'll see in a minute why. But for your own reference, sort of the white line here is the Arctic temperature for every year over like 100 years. The red and blue lines are sort of averages over the global ocean and over the global land. So you can see that the white line is much steeper than the other lines, again, that the Arctic is warming super fast. But I'm very interested in science communication. And I think I have a bit of a different way of going about science communication than others, in that I actually use data, and specifically data visualization, as a way to communicate climate change. My whole goal, and I'll talk about this at the end, is how can we sort of bring the science and make it more accessible? And my way is through visualization of real climate data. So for all of my presentations, I start off with this figure. And again, there's no labels because I just want you to really focus on the patterns and the colors. I'll give you some key clues that what you're looking at are lots of these circles. So they're little maps, and you're looking downward on the Arctic. On sort of the right side of each little map is Eurasia. And then on the left side is Greenland in North America. So I just want you to notice, what colors you see, what patterns you might notice, and then I'll add on some labels. So here's what you're actually looking at. And you're looking at observational data of temperature anomalies. And the word anomaly is sort of, we use it in a different way in climate science. Most people think of anomaly as being something, quote, like weird. But anomaly we use in climate science really to mean a deviation from average. So what you're seeing here is areas in red are temperatures that were warmer than average for a specific year. And I'm addressing years over our satellite records. So when we have observations from satellite data, which is from 1979 to present. So anywhere in red was warmer than average, anywhere in blue was colder than average. So now you can see that, sort of the pattern of the colors was going sort of from blue on top to red on the bottom. So that's your Arctic amplification. It's warming really, really fast. But there's, variability in each year. Not every map at the bottom is completely red. And that's because we have a lot of variability in a climate system due to natural climate variability or due to weather extremes. So again, the whole point of sort of my area of research is how can we figure out what climate change, anthropogenic climate change is causing the reds versus just sort of weather variability. So again, turning to the Arctic, you may have already started looking at this already, but I think it's important to re-look at what a map of the Arctic is, because this is a place, to be honest, where many of us are never going to get a chance to visit and don't frequently look at maps of the Arctic like I do. So again, you're looking downward here on the North Pole on the Arctic Ocean. So the Arctic Ocean is an ocean surrounded by land. So on the right-hand side of the map is, again, Eurasia, so Siberia, and then Europe towards sort of the bottom. And then on the left-hand side is North America, so Canada, Greenland, and Alaska all have borders with the Arctic Ocean. And then to sort of understand like smaller areas, the Arctic Ocean actually is broken up into different seas that have their own name, as you might see labeled there. And that's sort of how we talk about, that variability across the Arctic Ocean. So here's what you're looking at. This is really Arctic amplification kind of summarized together. So you're looking at, again, 40 some years of data. On the left-hand side, you're looking at temperature for each year from 1979 to 2022. The middle, you're looking at the extent of Arctic sea ice. And then on the right-hand side, you're looking at ocean surface temperatures. So what you might notice is that the temperature of the air in the ocean is rising and the sea ice is declining. And it's a quite linear trend as you're seeing here. And again, this is averaged for each year. So again, when we talk about this amplification word, it's this idea that the Arctic is warming a lot faster than average. So this is a bit more technical of a map, but I think it has it brings everything together. So really what you're looking at is anywhere that you see red shading, that means that that area is warming faster than the global average. So why I keep talking about this global average is because we often hear about it in the news. In fact, if you were paying attention to the news last week, you might have heard that July was the hottest July on record for the globe. So this is, sort of a key metric that we're always talking about in climate science, both in the science and communication. So then anywhere in blue is the opposite. So anywhere in blue is a region that's sort of not warming as fast as the global average. So what you can see here is that the top of the map in the Arctic is super red, so warming a lot faster than the global average. But there's one more key thing I want to point out here, and it's focusing on land versus ocean. And if you look closely, you might notice that there's a lot of red over most land areas. And that too is because the land is warming a lot faster than the global average. So that has big implications for where we live. We live on the land. So that means that our temperatures where society is located is warming faster than the global average we hear about like on the news. So it's something to keep in mind when you're thinking about things like heat extremes. So why do we have Arctic amplification? Well, this is a super complicated schematic, but I'm just showing it because it is complicated, and Arctic amplification is a complicated phenomena. There are a lot of things going on in the polar regions that is sort of the result of why it's warming so much faster. And it's because you have a lot of things interacting together. I think the one thing that I think makes climate science interesting and fun, but also challenging, is that you have to consider not just the atmosphere, but you have to consider the ocean. You have to consider the land, and how they're all interacting together causes these different feedbacks. So how do we talk about, ice? So I want to just go over a few key terminology that I'll be using throughout the talk. And one of it's being the extent of sea ice. So what that means is it's basically you look at the area of ice or the area of ocean that is covered by at least a fraction of 15%. This 15% number comes from people who work on satellite data. But anyway, so what it just means is that area, the fraction of that area has to be covered by at least 15% of sea ice. And then there's this terminology called sea ice concentration, and that's the actual fraction. So you could have an area that's covered by 5% of sea ice and 95% open ocean water. So there is a little bit of ice there, but we don't count it as far as that total extent. And then there's the thickness of ice. So this is what it sounds like. It's the actual thickness of the ice between the ocean and sort of the top layer where there's snow. So, without climate change, there is a seasonality of sea ice. What that means is that during the winter time, sea ice grows in the Arctic. It also grows in the corresponding winter time in the southern hemisphere around Antarctica. And then during the summer, it melts. So what you're seeing here is a super fast animation of the seasonal cycle of sea ice, just going through every single month. You can see it sort of pulsing back and forth. You can see, again, remember the hemispheres are in opposite seasons. So that's why you kind of see that opposite reflection going on there. So when we think about, taking into account declining sea ice due to things like Arctic amplification, we have to consider that there is also this seasonal cycle of sea ice. So I know I showed a very complicated schematic of Arctic amplification previously, but here's really the simple one that really what it boils down to. And I think if someone comes up to you and asks you what is Arctic amplification or why it's happening, I think this is the go-to explanation. And it's really that the ice is this bright white surface. And, it covers the ocean in the Arctic. However, we know due to human-caused climate change that the Earth is warming. So as the Earth is warming, it reduces the amount of sea ice. So it reduces that bright white surface. We call that albedo, means reflectivity. So what happens is that white surface is no longer there. And now you have this dark ocean water. And actually, the dark ocean is not very reflective, and it's a good absorber of heat. So instead of incoming sunlight hitting that white ice, and reflecting back out into space, it's now going deep into the ocean. So as it goes into the ocean, it's heating up the ocean. And then during sort of when sea ice begins freezing up in the wintertime, a lot of that heat then that was absorbed in the ocean escapes back into the atmosphere, which causes more warming. That more warming causes more ice melt, and then that's your feedback, your positive feedback. And that's really boils down to why we're seeing, Arctic amplification. So I've, showed you that previous graph of the temperatures are warming, the sea ice extent is melting. So you might say, okay, what about the thickness of ice? So what you're seeing here is a map of the thickness of the ice for every year, again, over since 1979 to present. So brighter colors mean that the ice is thicker. And so we're talking about, 4 or 5 meters of thickness of ice, back in the 70s and 80s, now reducing to less than half. The ice is now only like 1 to 2 meters thick in the last couple of years. And then the little bar that's going up and down, which is mostly going down, is showing the total volume of ice. If you sort of took the volume of all of the sea ice in the Arctic, so you can see that the volume of ice is rapidly reduced. Again, that's because it's thinning and the area of the ice is decreasing over time. Now, one other thing you might notice is that it's sort of not a continuously declining trend. It goes up and down a little bit per year. And again, this gets at the idea of why climate scientists look at trends, long-term trends. Again, there's year-to-year variability because of changes in like the weather. But the overall long-term trend is downward, and that is really climate change. So you might say, okay, I've only shown you, 40 some years of data. So that's not really that long in terms of Earth history. So there are lots of scientists who answer those questions, and they're called paleoclimate scientists, which means that they look at climate, climate histories of Earth over very long periods of time. They can go back millions and millions of years, using really cool methods to reconstruct climate of Earth's history. And they can do that for sea ice too. And I'm not a paleoclimate person, so I'm always amazed that they can do this. But, the people who work on the topic to reconstruct sea ice over thousands of years go up into the Arctic and they look at things like sediment cores and they look at things like tree rings and ice cores. And somehow they use these proxies to figure out how that correlates to changes in sea ice. So what the graph you're looking at here is 1,500 years of sea ice data. So what you're seeing here, that shading area is just like statistical uncertainty. And then sort of the mean of that, the average of that is that more brighter solid line. And then on the right-hand side, you can see where we are today. And then the dashed red line is from satellite observations. So we can match and make sure that the methods we're using in paleoclimate match the satellite data. They do match, giving us confidence that we can trust this type of data. And as you can see in the recent, couple decades, there has been a dramatic decline, and there's no decline like that in all of our paleoclimate history. So again, that the rate of change due to human-caused climate change is unprecedented in our climate records, even over these longer time scales. So I mentioned I work a lot with climate models, but I did get a chance in graduate school to go to the Arctic, and it was one of the best experiences of my life, so I always have to mention it during talks. And so where we went, I boarded a Norwegian icebreaker from a little island called Svalbard, which is off the coast of Greenland in the very sort of at the edge of the North Atlantic Ocean and the Arctic Ocean. What you're looking at here is a drone image from one of the drones that was on board the boat, and you're looking downward. So you can actually see our boat right there. You can also see big pieces of sea ice. The darker areas are actually open ocean water. So I think one thing that was really surprising to me is how broken the sea ice actually is. As you can see, there's lots of the dark areas of open ocean water. So what you do is you board your icebreaker, and then we drove it up into the Arctic further north. And the icebreaker sort of cuts through pieces of ice if it needs to. And then what it does is it looks for one of these bigger pieces of ice, and we called it an ice floe. And the boat actually anchors to the piece of ice. And then after it anchors, you actually get off the boat onto the piece of ice. And that's where you do all your experiments, like drilling sea ice or digging for ice core, snow pits, taking chemistry measurements and all sorts of different things. And that's sort of how you do field work within the Arctic. Here's a bit of a closer look. Now you can really zoom in on the boat. Again, the darker area is open water. The whiter area is sea ice with snow on top of it. So now you can see on the left-hand side sort of how you get off the boat. You can see our footprints of us walking around. You bring sort of a little sled with you with all your equipment that you sort of drag on behind you, and you do your experiments there, and so forth. Here's some of the experiments we did. So one of the things we do is we wanted to try to understand how the thickness of ice is changing. So we drilled ice cores. This is very different than drilling ice cores like in Antarctica or Greenland, in that the ice here, again, is only like a meter thick. So it's very much, an embarrassingly small amount of ice compared to the amazing ice cores they do, in the ice sheet areas. So where am I in this picture? So I'm actually in the back. So like I said, this was the best experience of my life. However, I realized that I am not very good at field science. I'm much better at a computer. So I was pretty terrible at operating the ice drill. So eventually they just gave me the notepad to take notes. And that's me in the back with the notepad watching everyone else. I had a lot of fun and learned a lot, but yeah, I'm much better behind a computer. Some of the other things we do these sort of snow pits, they're called. And why we're doing that is that because the snow, doesn't necessarily melt every single summer. So it actually can layer on top of the sea ice. So when you sort of create these pits, you can actually sort of, again, reconstruct a few years of sort of weather data. And one of the interesting things we found when we were sort of digging into the snow was you could see that last year there must have been smoke from wildfires in North America, but because we found a layer of soot, sort of black specks within the snow, which we think was from wildfires. So anyway, we try to dig these pits to understand how deep the snow is and look for things like, wildfire soot. So again, that was one of these awesome experiences in grad school. They always say when you're looking, exploring, even in, you get into your niche field of your PhD, to try something new. And for me, it was, getting experience in the field. But now I'm going to talk about more what my actual sort of PhD research was about. And it was really trying to understand, our changing Arctic compared to weather. So sort of my background is that I was very much a weather nerd growing up. Even in elementary school, I was giving the weather over the morning announcements. And I went to undergrad thinking I was going to be a forecaster at the National Weather Service. And then I just, again, one of those things, you try something new. So in undergrad, I reached out to a professor and said, I don't know anything about research, but I'd like to try. And he said, sure. And I realized after that project that I was very interested in climate research, specifically understanding how does climate change affect the weather. So I was very much tying my interest to the weather through climate change. And so, of course, the Arctic, as we've gone over, is this area that's rapidly changing in terms of the ice, in terms of how much it's warming. So, we have this area at the top of the world that's going under this, so much climate change. How does this affect the rest of the atmosphere and circulation? So that was the question I tried to address in my PhD. And this question became really popular in sort of the 2010s, you could say, when there was a series of super strong winter storms, particularly across the northeastern United States. They had nicknames like Snowmageddon in Washington, D.C., and it was a constant couple winters in a row where they were just receiving, severe cold outbreaks and feet of snow at a time. So there was a question, how can we possibly be getting these really severe winters when climate change, we know, is warming our planet? And perhaps, is there a linkage between the Arctic and this cold weather? So why there might be a linkage is due to something called the jet stream. You can just think of the jet stream being these really fast winds high in the atmosphere that sort of guide, storm systems and air masses all around our planet. So when the jet stream kind of gets, wavy, it allows cold air to sort of come southward into the United States. So the question is Arctic climate change causing the jet to sort of change its position, which would allow more of these extreme winter storms? So, this question also got more interest. Now we're looking at a more technical slide here. So what you're looking at is the trend in temperature over different periods. So what you're looking at on the left-hand side is 1980 to 2021, and on the right-hand side, you're looking at the trend in temperature, 1990 to 2014. Red means it's warming, blue means it's cooling. So if you look on the right-hand side through 2014, over this period since 1990, you might say, whoa, this is during winter time. I should have clarified that there's actually some areas, particularly over land, that are cooling over this period. And then in the middle, where the Arctic is, it's rapidly warming. So are these things connected? However, this is a really good lesson in why climate scientists, need more and more longer data records. Because as you can see on the left-hand side, if you take this trend over a few additional years, that blue, those blue areas really disappear. So anyway, this has been a really active area within climate science research to understand if these things are connected or if this was just due to sort of natural variability, just noise and sort of statistics. So as I said, there's been tons of research on this topic. So when you start graduate school, your first year, you're taking classes and you're reading. You're reading lots and lots of papers on whatever your topic is. And in my area, connecting the Arctic to extreme weather, there were tons of papers to get started with. So I'm just showing you sort of, an overview of these papers. Pay special attention to the titles of these. They're much ambiguous titles. For example, why are Arctic linkages to extreme weather still up in the air? So all of these titles are very much like, what is going on and why can't we figure it out? So, going forward, over time, you can see more and more, work on this topic. And then the most recent sort of review paper on this topic came up with this title, which makes me laugh, which is called Divergent Consensus on Arctic Amplification Influence on Mid-Latitude Severe Winter Weather. And I'm not 100% sure what divergent consensus means, but in summary, it means that we still have a lot to learn. So if you're interested in this topic, I'm sure there's plenty of PhDs you could do investigating this topic. I'll also point out that, in addition to just over the last decade that this has been an interesting topic, actually it stretches back even further to one of the earliest climate models ever built. So this is from a research study in 1973 that actually had a very early primitive climate model. And all they did was run a climate model and they remove all of the ice in the Arctic to see what happens to temperature. So this is a graphic from the paper. I've added the colors to help make it a little more clear. In the middle, again, you're looking downward at the North Pole. So you can see that really familiar pattern that we saw in one of those earlier maps, where the Arctic is warming, but, sort of lower latitudes over land are cooling. So this was, one of the first, investigations that say, hey, maybe they're connected. Maybe the Arctic is causing more extreme winter weather like where we live in North America. So the motivation for my research was really to understand this topic, specifically about Arctic sea ice. So there's many different directions you can focus on it, because in addition to sea ice affecting the weather at lower latitudes, and lower latitudes being like North America, Europe, and Asia, the weather also can affect the sea ice. So my research focuses on it one direction to help simplify things. So it's sea ice affecting weather. Then you can look at historical, what has happened in the past or in the future. How is it expected to change in the future? I focused on the future. So you might ask, okay, so why might these be related? So I'll dive really quickly a little bit into the science using the drone image I showed you earlier of our boat. So remember I said that, the areas in white are sea ice, areas in dark shading are open water. So this is really important, because what's happening here is where there's no sea ice allows the ocean to be touching basically the atmosphere. And what that does, think back to Arctic amplification, is that there's a lot of heat in the ocean. So, the ocean is warmer than the atmosphere. So what happens is you actually get a flux of heat coming from the open ocean to the atmosphere. So that's called a turbulent heat flux, if you want the technical word. So this is one reason, that we want to try to understand how much open water is in the Arctic because of this heat that's coming out of it. But also, there's another sort of area of heat, and that's due to the thickness of ice. So if you have really thick ice, it essentially is like a blanket preventing the heat in the ocean from getting into the atmosphere. But if the ice is much thinner, then that heat actually can escape. So we know that because of climate change, the ice has thinned, which allows some of that heat actually to move through the ice, sort of a conductive heat flux from your physics classes. Okay, so you might say, well, that seems pretty straightforward. We have all this heat coming up, and, we've seen these early model experiments from the 70s showing they might be connected. Well, as we've said, we know from climate science that everything in the Earth system is connected. So here is just a schematic I tried to put together from sort of my research to try to emphasize of how many complicated interactions are going on. It's not important to really remember any of these other than to know that this topic is super complicated. And it's because that in addition to changes in the sea ice and the changes in, the air temperature of the Arctic, other parts of our planet are also experiencing climate change. So trying to understand how climate change in other areas might also be affecting things like the jet stream can then affect, all of these linkages. So very complicated setup. So I'll just show the results from just one of our research studies. In this one, we tried to compare how does sea ice loss alone compare to the whole effect of Arctic amplification on this linkage between, cold weather during the wintertime over North America and Europe versus, the warming Arctic. So what you're looking at here is a very technical plot, I realize. But I just want to introduce you to some of the research that I do and we do in climate science. So what you're looking at here is we ran climate model experiments. On the top row, we essentially really heated up the Arctic. We heated the Arctic not only at the surface, but also vertically, because we know that the atmosphere also has structure. So in that top row, we just sort of really heated up the Arctic temperature. On the bottom row, we left the temperature the same, but we changed sea ice. So in this case, we sort of reduced the amount of sea ice in the Arctic. And what we wanted to do was wanted to compare which of these effects has more of an influence on temperatures in other areas. Again, Asia, North America, and Europe. So if you look at the sort of circle, the map in the upper right, you might notice that you can see some areas of blue. The black dots, what that means is that's statistically significant. So we can say that this is a robust temperature change. So in that case, where we looked at climate change at the very end of this century, due to Arctic amplification, we did find a sort of robust cooling effect. So basically what this study really wanted to do is try to understand how much of this is caused by sea ice, this relationship, versus temperature. And in this case, we found the temperature had a much larger role, even though that sea ice is linked to it too. Okay, so, I want to now move into sort of projections. So what does climate change look like in the future? So what you're looking at here is an animation from a climate model that's going around and around through the end of the 21st century. So you might notice at the very top there is this blob, and that is the warming Arctic, which is warming a lot more than the rest of our planet, but which is also warming, and as I've said, it's warming more over land areas. So that's our planet without change. And we use climate models as sort of a tool to try to understand how it's going to change in the future. We don't just run these climate models and just say, okay, this is what's going to happen. There is, whole areas of research done to evaluate how well climate models are doing. And what I mean by that is how well do they reproduce temperatures of what we are doing today? Because if they can't, reproduce today, how are they going to reproduce, predict into the future? So what you're looking at here is one of these sort of evaluation methods we look at. This is a graph of temperature. The thin lines, the red and dashed blue lines, are data sets from the real world, from observations. And then the white and gray shading is from our climate model, with some shading due to uncertainty in the climate model. So the goal here is if the red and the blue lines stay within the gray shading, and this is looking at period from 1950 all the way to present, you can see, yay, they do, which means that our climate model here that we've looked at is doing a really good job in reproducing the temperature of the real world. Again, giving us confidence that the climate models know what they're doing, and we can learn something from them about the future. So I want to go through an experiment. This is an experiment that, a lot of climate scientists do to show that climate change is caused by humans. And I'm going to use this example in the Arctic. Okay, so this is a graph that I'm going to be going through. The x-axis is year. The y-axis is that temperature anomaly. So temperatures compared to average. The yellow line here is real world data. So you can see there's squiggles. That's your year-to-year variability, but in the last, at the very end of the yellow line, it's going up, climate change. Okay, so that's your real world observations. Now let's run a climate model and let's try to simulate those real world observations. Again, yay, the yellow line is mostly within sort of the blue spread. That means our climate model is doing pretty well at reproducing temperatures over the last, 100 years. Okay, so what if we run the same climate model and the only thing we do is we remove human-caused climate change? So no changes in CO2, things like that. What happens? That's what you see in the gray line. And you can see it's flat. There's no upward trend. There's no climate change. So without, inducing greenhouse gases, carbon dioxide, we do not see Arctic amplification in sort of a world without humans. Okay, so as I've already said, you can compare the blue and you can compare the gray lines. We can see that the blue line, which has things like carbon dioxide, matches the yellow. And you can see that they sort of diverge around 1990, meaning that sort of human-caused climate change really started to take a big role in Arctic climate around 1990 or so. And it's only accelerated since then. So what about the future? So what about a world where we actually increase fossil fuel development? That's what you're seeing in the red. And I know it might be hard to see, but on the y-axis, basically temperature change so far has been about 2 degrees Celsius. If you go look at the top of the red line, it goes up to 14 degrees Celsius. So this is a future that would dramatically change the Arctic. Okay, so what if we, sort of reduce greenhouse gas emissions? We have other sustainability goals, but we only do it sort of at a moderate level. What does Arctic climate change look like? That's what this new red line is. That's about 6 degrees Celsius of warming. So it's more than double what we've already experienced. So again, the Arctic will dramatically change if that's the case. But what if we start really rapidly reducing emissions over like the next 5 to 10 years? Pretty quick, we'd have to do this. Then this is sort of this tan line here, and you can see that the Arctic still warms, but it actually begins to decline the temperature by the end of the 21st century. So you can see that depending on our choices, this is dramatically going to affect what the Arctic looks like in, even in 2060 per se. So this is a huge spread in the amount of warming. In my message here, and I take this from a Ginger Z, if you've ever heard of her, she's a meteorologist. I think she's now with ABC, and she has this really great show called It's Not Too Late, thinking about sort of climate change solutions stories. And that's my message here. It's not that, this horrible outlook for the Arctic, but it's actually that there's quite a lot of spread depending on the choices we make over the next decade or two in particular. So this also means a lot for sea ice. So I often get the question of, are we doomed to have an ice-free Arctic in the near future? And actually, my answer is no, we are not locked in. And there's been people who run climate model experiments to simulate this. And basically, that sums up to, if we reduce greenhouse gas emissions very soon, we can really reduce the likelihood of experiencing an ice-free Arctic. So if the takeaway message here is that sea ice is not necessarily doomed yet. One other area that I just wanted to touch on, because I know it's sort of a very popular topic in the news right now, and it's artificial intelligence. And admittedly, I use it very different than what you're hearing about it in the news. Basically, you can think of just artificial intelligence and machine learning as statistics, where you take lots of data, you run it through this statistical algorithm to make a prediction. So one of the areas that we've been really exploring recently is how to use these sort of statistical methods to evaluate our climate models. So something I've been working on more recently is sort of looking at maps of different climate variable data, like in the Arctic. So in this case, I have like a map of temperature, and I have a map of temperature coming from real world observations, and I run it into this statistics, this machine learning, and what it outputs is it tells me what climate model best simulates that temperature map. In other words, which climate model looks closest to the real world. And this is very preliminary work that we're exploring, but artificial intelligence, when you hear that in the news, there's a lot of different ways it's used in science, very different than often, what you hear in the media. So this is one, I think, pretty cool method that we're doing right now to explore how we can use this to evaluate how well our climate models are doing. So the last thing I really want to get into is the area that I'm interested in about science communication. In short, I do a lot of science communication, maybe more than my supervisors would like me to do sometimes. And, when I started going to thinking about science communication, you go to a lot of workshops on it, and people would often say, never throw facts and numbers at people. And I often thought to myself then, like, oh no, what I'm really doing is I'm creating graphics, I'm creating graphs and animations using data and throwing it at people. I'm like, oh no, I'm doing exactly what they say not to do. But I've since come to realize that actually visualizing data can be a form of storytelling. And hopefully I can show you some examples of why I think this is. So I want you to imagine you're looking at lots of data. So just tons of numbers, all of this data I've been showing you in maps. This is what it looks like in the raw. We use tools, computer coding tools, to make these pretty maps, but it's essentially just lots of millions and millions of numbers, and we need to make sense of it. So one of the, as we've introduced, one of the main metrics of climate change is global temperature. And this was one of the most creative things I had ever seen from a few years ago. And it's by a climate scientist named Dr. Ed Hawkins over in the UK. And he posted this on Twitter back in like 2016. And I spent too much time on that website and was actually, I think, online when he posted it. And I thought, wow, this is incredible. This is the coolest graph I've ever seen of temperature, which normally is just a line going up. So what you're looking at here is the temperature for every month since the 1800s all the way through present. And as you can see, it's spiraling outward. And that's because the climate is warming. So it's sort of this further and further it gives outward, it's more and more warming. So I thought this was a really powerful way to visualize this data. And admittedly, I guess a lot of other people thought so too, because this climate spiral was actually featured in the opening ceremony of the Rio Summer Olympics. And asked me before this, and I never would have imagined that a graph of climate data would be featured in such a big venue as like the opening ceremony of the Olympics. And if you're interested in, more about this, he has a really awesome article about thinking of creative ideas with data and how that can really resonate as a form of science communication. So another cool way that Ed Hawkins has also done visualizing global temperature is this image. And this is called the climate stripes, which you may or may not have also seen. So what you're looking at here is every vertical stripe is a year of global temperature, where darker blue colors mean it was a colder than average year, and then redder colors mean it was a warmer than average year. You're going from years from left to right, older years on the left, recent years on the right. So this is a really, unique way of showing basically that the Earth is warming. The red colors are on the right-hand side. And these climate stripes have gone crazy viral. They have been basically everywhere you could imagine. I've seen them on clothing lines. I have a coffee mug right next to me right now with the climate stripes. I've even seen people post it or like paint their car the climate stripes. So it's been a really awesome way to communicate climate data to really accessible and broad audiences. However, there was some pushback from other scientists. So I'll explain in a minute why, but I wanted to put out this reminder, and this is a reminder that I always tell myself when I'm working with climate data for science communication is stop thinking like such a scientist, but keep in mind that you are a scientist and that you are an expert with data. Everyone who works with large data is, in my view, a data scientist. So how can you leverage these two sort of concepts, which often oppose each other? How can you leverage, their sort of advantages to really think of creative ways to talk about climate change? So Ed Hawkins created then this visual because of the pushback from other scientists who said, whoa, how can you share a graphic of data with no labels, no axes? So he created this one, which added a few little labels. There was still some pushback, so then he's created other versions of these climate stripes with more defined axes. However, these graphics, which look more like typical graphs, have not resonated with non-experts nearly as much, I think for obvious reasons. This is just keeping in mind, again, to stop always thinking about being such a scientist. And if you're interested in these climate stripes, you can generate them for every country and state all across the world. And this is a really awesome way to sort of open up any presentation you might give in the future. Highly recommend checking out this website to look at your own climate stripes, maybe where you're originally from too. So, in addition to that sort of example of how we can use data to talk about climate change, I also wanted to show another one of my favorite examples, which it was the cover of a magazine for sort of in the field of weather, which essentially took real climate data. And this is an artist, Jill Pelto, and she took the real data and she used her expertise in watercolor paints to create this image on the left-hand side, which is actually visualizing, data over time to show different climate variables, things like changes in sea level and loss of glacier ice. And I think this was just a really awesome way of how we can, use data about climate change and take into account creative forms of art and visualization to do so. And why I think this is important is we know that climate is changing in real time, and the Arctic in particular is changing now. This isn't something in the future, it's happening right now. And this is really an opportunity to communicate all of this. So for sea ice, I said there was a seasonal cycle. So a couple years ago, most news outlets would only publish 2 stories a year about sea ice, one at the end of winter at its maximum and one at the end of summer at its minimum. But we've realized if we talk about climate change data in real time and talk about things like changes in sea ice, what it's doing day to day, we can actually realize that there's a lot of extremes happening all throughout the year. And it's not just, scientifically interesting. These extremes are affecting people within the Arctic. And now we're seeing, an increase in the amount of sort of coverage in the news of changes in Arctic sea ice to sort of non-expert audiences. And one example of, one of these changes that happened randomly in the middle of the year was back in 2018 in a region called the Bering Sea. This is an area located at the North Pacific Ocean between Alaska and Russia. And this is a really important region because there's a lot of indigenous communities that are located along the Bering Sea. And during 2018, in the middle of winter, all of the sea ice basically melted. And this really had huge impacts both to communities in the Arctic, but also to sort of the ecology of the ocean and marine ecosystems. And this was a great example of, tracking this in real time, sharing this data to non-experts as it was happening to raise awareness about the big impacts that Arctic climate change is having on people. And I think this is a great example of how we can use data to start climate conversations. And I'm all about, we don't need just scientists to talk about climate change. We need people working in all aspects of this area to really communicate what's going on. So I realized, I hope I hit on a few of your questions that you sent. I really appreciate you sending them. So there was one thing I added because there were a couple of questions about this, and it was sort of, how can we better understand sort of fossil fuel emissions and how is it tied to things like sea ice loss? So this was a really great questions, and there is a really good example about this from a study from a few years ago by very much sort of the sea ice experts. And they found that there was this direct linkage between sea ice loss and anthropogenic carbon dioxide emissions, and that it was like perfect linear relationship between increasing carbon dioxide and more sea ice loss. So there is this new tool from this organization that's called Arctic Base Camp. I put the link here and I'm happy to share the slides if you're interested in, which what you can do is you can actually go to this website and you can locate your city. So I'll go through an example here. So I'm located in Princeton. So it found these different industrial sectors in the Princeton area. So I just randomly picked aviation as being a sector. And one of the areas that is close to me is the Newark International Airport. And what you can do, I clicked on a few different things that it'll ask you to but what it actually does is it relates the amount of emissions from these different industries, and it will actually show you how much sea ice was sort of essentially melted from that CO2 emissions. And if you look really closely, of course, I realize you're not in Princeton, but the red area is actually a map of downtown Princeton, the orangish area, and then the blue area is the area of sea ice that melted and that would essentially be covered, by open oceans. So they actually show you on a real scale, correctly scaled map, this relationship between all of these different industries and companies and the amount of sea ice loss. So this is a really interesting visualization tool that's interactive and a good sort of talking point if you're interested in it. So I will end here and just say that, as you've seen, climate change has already emerged in the Arctic. If we continue to work on improving our observations and climate models, and there's a lot of awesome climate science research that still needs to be done, we can really reduce uncertainties, better understand impacts in the future. But I want to stress that depending on the choices going forward into the future, we can still prevent a lot of the worst impacts of climate change within the Arctic. And hopefully there's a little bit of time for questions. So I'll stop here. Thank you.
Thank you, Zach. As always, very informative. I always learn something. I'm like taking notes, like I'm in a seminar. Really great. So if any of you have any questions for Zach, I know he did address some of your questions that you had come up with in advance, but if you have a question now after listening to his presentation, please feel free to add it to the chat. I did have a question, I think. Looking back at some of your earlier plots, there was like 2015 maybe was a pretty anomalous cold year over the Arctic. What was going on then?
Yeah, this is a really good example of like weather. So I realize I'm a little biased because I've always loved the weather. So I always stress how important understanding of the weather is. But I think it really gets at this idea of, when we track climate change, we kind of think that, okay, every year is going to be warmer than the next, but that really isn't the case. And it's due to things like changes in weather. So, in short, not every year globally is going to be the hottest on record. And that's because, you can just have really weird things happening in the weather that cause one year to be a bit cooler, like 2015, which was a bit colder. And, a few years before 2015 was this year 2012, which was the lowest amount of sea ice ever recorded. So people at the time thought, oh my goodness, we're really dropping in ice. But no, step back for a second and realize that changes in the weather can sort of accelerate the trend briefly or decelerate it. And I think that's why I'm so passionate about how can we use climate models and other tools to understand what is climate change, what is weather, and how does that affect every single different year.
Yeah, great. Just because it's in the news, can you give us a very quick understanding of why Antarctica is seeing such a very, very low amount of sea ice in the middle of winter?
Yeah, that's a really tough question. So I am very passionate about answering I don't know. It's interesting. I could talk about this a lot, but I think we really don't have a good understanding of what's going on in the Antarctic. So essentially, unlike the Arctic, there has been no clear trend in sea ice loss in Antarctica. One of the really simplest explanations is that, like I said, the Arctic is an ocean surrounded by land. Antarctica is land surrounded by an ocean, and it's a really high area of land. The Antarctic ice sheet is super high in elevation. Because of this difference in landmass and ocean affects climate change differently. However, all of a sudden this year, we've seen like unprecedented low amounts of sea ice. Like we have no historical record that I know of that looks even close to this year. So the question is, of course, like I've been summarizing, how much is this climate change versus weather? And I don't know. And I think no one knows right now. But there are a lot of, great people working on this topic that will hopefully have answers soon. And they're doing things like running climate models, which takes time because of supercomputers. So I don't know. Ask me again in a couple months.
Yeah, thank you. Okay, so one last thing is a lot of the students in this class may not, end up being an Earth system scientist. So what type of other careers do you see in this field, right? You mentioned like educators and artists, but you mentioned machine learning. Like what is the need for computer engineers? Like, so can you just give a sense of like what career paths and what careers do you work with at NOAA?
Yeah, so I'll go in two directions. I'll start with first the data side of things. So we're at a point where our climate models and satellite observations and real world observations are producing so much data that we really don't have enough people right now to look at it all. And we need people looking at it, not just necessarily always from the scientific point of view, but also people who are experts in computer science, who are experts in, data engineering, who can really analyze this huge amount of data that we have. In fact, climate science, to be honest, is one of the sciences that produces the largest amount of data. And we really need people who are experts in analyzing that. I'm not, I do some machine learning, but I'm not a computer scientist. I don't always know what I'm doing when I'm analyzing all this data. So we need so many people in engineering, computer science to analyze it all. So on the other side of this is that we need a lot more people in social sciences. So understandably, every climate change talk I get asked about solutions and what does this mean for people? And I have my kind of go-to answers, but to be honest, I'm not trained in, solutions or trained on, things like renewable energy. And I'm not trained on people. I'm not a social scientist and I don't want to pretend I am. So we really need a better understanding of people who work in social sciences to understand one, impacts. One thing about climate change is that the most vulnerable communities are also more vulnerable to the largest amounts of climate change. And we need to really understand that. We need people working to understand how these areas are most at risk. We need to understand impacts, like how can we mitigate climate change and adapt, and not just through the physics of it, but also, again, social sciences, like what happens if we start seeing sea level, start causing major problems for a huge city or sort of an area that's really vulnerable, like in Southeast Asia, like in Bangladesh. And how does this affect, do people need to move to new locations? What does this mean? So we need people in social sciences. And lastly, we need communicators. We need communicators of all different kinds. I really, as hope I've shown, I don't think there's one perfect way to communicate climate change. It's not just through human telling stories. It's not just through data. We need people coming at it from all angles to reach, broader audiences. So I think you can find somewhere in every single field to work on climate related topics. That's how big of a global problem this is. So I think if you're interested in climate but don't see a path through, I think there is a way, actually.
Awesome. Thank you. Okay, so let's all thank Zach, maybe in the chat, give some applause. I really do appreciate your time. It was really a pleasure. And yeah, so other than that, everyone, that's it for today. And Zach, can you send me the slides just so the students can have those to look at your links and whatnot as well? And yeah, students, there is no live lecture on Thursday because I'm traveling. I've recorded that lecture. It's on my courses. So I will send you some updates my courses through Canvas. I will send you those updates this evening. But otherwise, I'll see you all next week. Thank you.
Hello.
Hey, Jared.